In the previous video, we derived the Euler equation for a functional with two independent variables. So this is now a two-dimensional case, and we can see natural extensions to 3D as well. And we saw the Euler equation results in a partial differential equation. So in this video, we're going to do an example to illustrate how this works in this specific example. So you can see here we have our functional I of a single dependent variable u, but now that dependent variable is a function of both x and y. So it's a double integral over x and y, so dx dy, and the integrand is 1/2 times the square of partial u partial x plus partial u partial x times partial u partial y plus u squared plus 2 times x times u. And we'll do this example in both ways, just as we've done for some of the previous examples. We'll first take advantage of the fact that we know the Euler equation for this particular template of a functional, and then we'll pretend that we don't know it, and we'll take the variation of I and set it equal to 0 and go through the integration by parts and so on. And the domain, you can see here, goes from x equals 0 to 1 and y equals 0 to y equals 1 as well. So this is a square domain. You can see it here in the x, y plane. The boundary conditions on the left-hand side when x is equal to 0 will be specified as 3y, and on the bottom when y is equal to 0 will also be specified as 2 times x. The other two boundaries will be natural. So this is fixed, and then these two are natural and natural. So we'll first do this example taking advantage of the fact that we know the Euler equation for this form of a functional. And so that involves evaluating partial f partial u, partial f partial u sub x, and partial f partial u sub y. Here is that Euler equation that we just derived in the previous video. So we take the partial derivative with respect to u. There's no u's in this term or this term. The partial derivative of u squared is 2 times u. The 2 cancels with the 1/2. And then the partial derivative of x times u with respect to u is x. So we have u plus x. Then partial f partial u sub x. There are no u sub x's here or u sub x's here. Here we have u sub x squared. So the partial derivative of that with respect to u sub x is 2 times u sub x, and again the 2's cancel. And then we have u sub x times u sub y. Partial derivative of that with respect to u sub x is u sub y, and then don't forget the 1/2. So u sub x plus 1/2 u sub y. And then finally with respect to u sub y, there's no u sub y's here, here, or here, only here. The partial derivative of that with respect to u sub y is u sub x times 1/2 times u sub x. So we substitute those in here, here, and here, and then we can evaluate these partial derivatives and simplify a bit, and we get partial squared u partial x squared plus partial squared u partial x partial y minus u is equal to x. So this is a second order. It's a linear, non-homogeneous partial differential equation. Because it's a partial differential equation, we often cannot solve it, so the step 3 in our 3-step process will typically have to leave for another day. So we're content typically with getting the Euler equation and the corresponding boundary conditions, as we will here. So that's the Euler equation. And then the boundary conditions. We know that they are fixed on the left and the bottom, so x is equal to 0 and y is equal to 0. So those are done. No need to do anything there. But now we need to evaluate the natural boundary conditions on the right boundary when x is equal to 1, and on the top boundary when y is equal to 1. So from the last video, the natural boundary condition is partial f partial u sub x times dy ds minus partial f partial uy times dx ds is equal to 0. And remember, these derivatives are related to the dx, dy, and ds as we go along the boundary C that bounds the area A, that's our domain. So let's walk through this for each of these two cases on the right and the top. Now remember that ds is a little infinitesimal piece of C as we go counterclockwise around the bounding curve C. So keeping that in mind, for x is equal to 1, so that's on the right side of our boundary, dx will be 0 because it's a vertical line, so there's no dx, and dy will be ds. dy is up because y is positive up, and ds is up because we're going counterclockwise around our domain. So then if dx is 0, dx ds is 0, and the second term vanishes, and then dy is equal to ds, so dy ds is just 1. So we're left with just this term here is equal to 0. So we have partial f partial u sub x times 1 is equal to 0. Well, we have partial f partial u sub x. We evaluated that back here to get our Euler equation. So that's u sub x plus a half u sub y. So that's partial u partial x plus a half partial u partial y is equal to 0 at x is equal to 1. So that is our boundary condition, natural boundary condition, along the vertical right side of our domain. Let's do the same thing for y is equal to 1. So this is across the top. So dx is now equal to minus ds because dx is positive to the right, but ds is positive to the left. We're going counterclockwise around our square domain. So dx is minus ds, and dy, because this is a horizontal portion of the boundary, dy is equal to 0. So dy ds is equal to 0, and dx ds is equal to minus 1. So again, we go back and evaluate our natural boundary condition. Dx ds is equal to minus 1, and dy ds vanishes. So we need partial f partial u sub y. Once again, we evaluated that back here. That's a half u sub x. So we have partial u partial x has to be equal to 0. Along the top boundary, y is equal to 1. So again, we have our natural boundary condition now along the top. We have the two Dirichlet or fixed boundary conditions, and then we have the two natural boundary conditions as well. So that's the full statement of the problem. Once again, we typically won't be solving these PDEs. We would normally need to use numerical methods to do so. So just for practice, let's look at this same example again, where we take the variation of I and set it equal to 0. We'll get the same result in the end, the same Euler equation and boundary conditions, but it's good practice to try this every once in a while, even when we don't need to, because we know the form of the Euler equation. So I've just repeated the functional here and the two fixed boundary conditions, and then we're going to take the variation of I and set that equal to 0. So here we go. So variation of the integral is the integral of the variation for the usual reasons, because our boundary doesn't vary, it's fixed. And so I take the variation of something squared, that's 2 times the something times the variation of the something. So that's u sub x times delta u sub x. Then the variation of u sub x times u sub y, we use the product rule. So that's u sub y times delta u sub x plus u sub x times delta u sub y. And then something squared again. So that's 2 times u times delta u. And then 2 times x times u, variation of that. The x does not vary, only the u varies. So that's 2 times x times delta u. And then, of course, don't forget the 1/2 out front. That cancels a bunch of those 2's. So now what we want to do is to gather all the terms for each of the variations. So we have a variation of u sub x here and here. We have a variation of u sub y here. And we have a variation of u here and here. So we pull together everything multiplied by each of the variations. So these are the terms multiplied by the variation of u sub x. This is multiplied by the variation of u sub y. And this is multiplied by the variation of u. So let's take a look at each of these 3 terms. So this term we're done with because we have something multiplied by the variation of our dependent variable u. So that's exactly the form we want, so that term is done. In this term, we have something multiplied by partial y of the variation of u. So we need to get that partial y off of that variation. Same thing here. We have partial x of the variation of u, so we need to get that partial x off of the delta u. And then we can gather everything together to get our Euler equation as well as our natural boundary conditions. So we need to use integration by parts in order to take care of these derivatives. Now remember, in the general case that we looked at in the last video, where we have bounding curves that can be of any shape, we had to use the divergence theorem. Here, because our bounding curves are all straight lines, horizontal and vertical lines, we can actually just use the good old-fashioned integration by parts as we normally do. So let me show you how to do that. The key is that in this case, for example, we're just moving the x derivative off of the delta u. So I can do the integration by parts to accomplish that. So you can see I've color-coded these. So we have this term, and that results in this term evaluated at the endpoints from the integration by parts. That's the p times the q, the integration by parts. And then we have these 2 terms. And these 2 terms are partial x of this, because remember, we get the partial x off of the delta u and move it on here. So that's a minus uxx minus a half uxy, remembering the minus signs from the integration by parts. Similarly, for the blue term here, that's a partial y. So that partial y gets moved over here. So that's a u sub xy, so partial squared partial x partial y. And then we get the term evaluated at the endpoints. Now in this case, it's y is equal to 0 and y is equal to 1. So this is application of the divergence theorem as we did in the more general case. So because the boundary is just horizontal and vertical lines, we can do the integration by parts in the usual way. So you'll notice now we have something times delta u, something times delta u, and something times delta u. These first two are evaluated only at the boundaries, so those are going to give us natural boundary conditions. And this one is evaluated throughout the entire domain, so that gives us the Euler equation. So that's what you see here. Here's the Euler equation. U sub xx plus u sub xy minus u is equal to x. And that's just a simplified version of this. Once again, it's a second order, linear, non-homogeneous partial differential equation. Then we have the natural boundary conditions. Partial u partial x plus a half partial u partial y has to be equal to 0. That's what you see here. And then partial u partial x has to also be equal to 0. And that's what you see right here. So again, you get the same result obviously in the end, but it's good practice to do these sometimes by taking the variation setting equal to 0, following through with the integration by parts, so that in cases where we have to, we're comfortable doing it. So this last point here is the one that I emphasize, that normally in the 2D case, we have to use the divergence theorem, but because of the rectangular nature of our domain, we could use the 1D integration by parts in the x and y directions independently of each other.